Good afternoon, everyone. I hope you are doing fine. Welcome back to FilSciHub, and as promised last week, this week we will be tackling the conservation of linear momentum. Before we proceed with our content standards and MELCs, let me introduce myself again. I am Mark Cortez, ABS Mathematics and Science teaching graduate from the University of the Philippines, Los Baños, and a chemistry and physics module creator for FSH Ed. You already know the drill. Before proceeding to our learning guide, let us first take a look at our content standards. Content standards, the learners demonstrate an understanding of impulse and momentum. So for this learning guide, we will deepen our understanding of impulse and momentum through our MELCs, or most essential learning competencies. Infer that the total momentum before and after collision is equal. Specifically, a discussion on the law of conservation of momentum. Now, before we proceed into discussing how exactly momentum is conserved, let's first take a look back at last week's discussion. So, let's have a review and connect. Last week, we discussed momentum and described it as mass in motion. Mathematically expressed as small letter p is equal to mv, with the standard units of kilograms, meters per second, and we discussed that it is a vector quantity having both magnitude and direction. Additionally, we also discussed the definition of impulse. We said that impulse is a change of an object's momentum. It can be mathematically expressed as I is equal to force times the change in time. We also said that it is also a vector quantity, say, with both magnitude and direction. And lastly, we were also able to discuss how these two quantities are related, specifically how the impulse on an object is equal to its change in momentum. Through this theorem, we were able to derive the value of force based on the change of momentum. Now, keep this in mind, or keep this equation in mind, for we will use this later on in our sample problems and discussion. The law of conservation of momentum states that for a collision occurring between object A and object B in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. That is, the momentum lost by object A is equal to the momentum gained by object B. So para maintindihan po natin ito, let's dissect it. Himayin natin yung law na ito into its different parts. So first off, let's first define what an isolated system means. So an isolated system is not affected by external forces that changes the momentum of the system. So we have here in our slide, or in this example, is a box that represents our system. And it isolates objects A and objects B with their corresponding momentum. So object A has a momentum of 300 kilograms meters per second, while object B has a momentum of 0 kilogram meter per second. So if we have here now an object C, a different object outside, so we have object C with a given momentum, hindi natin siya i-consider since it's not part of our isolated system. Okay, so we will only be looking at the forces, specifically at the momentum of object A and object B inside this system. Okay, and how do we get the total momentum in a system? So we simply add the momentum of each object. So we have this formula: P total is equal to the momentum of A plus the momentum of B. Okay, now this is for this exact system and scenario. However, if we have a larger system and we have additional objects to consider, we will also have to include their corresponding momentum. Now, the next part focuses on before and after collisions. The momentum of the two objects before and after collisions. So we have here two scenarios: before collision and after collision. So these are the same system. So we still have object A and object B, object A and object B. And we can observe that In the before collision, so before each object makes into contact with each other, we have object A with a momentum of 300 kilogram meters per second approaching object B with a momentum of 0 kilogram meter per second, meaning it is not moving. So si object A ay gumagalaw and si object B ay hindi gumagalaw. Okay? So object A will be colliding with object B. So, pero this is before, so papunta pa lang siya. Wala pa silang contact with each other. So the total momentum in this scenario is 300 kilogram meters per second. As I've said earlier, in order to get the total momentum, just simply add the momentum of the individual objects. Okay? Now, in after collision, so let's say nagbanggaan na sila, object A has a new momentum of 0 kilogram meters per second. So it stopped. It totally stopped. While object B rather, got the momentum or gained a momentum of 300 kilogram meters per second. So siya naman yung gumalaw. And we can see that the total momentum in this scenario is still 300 kilograms meters per second. Which leads us to the last statement of the law, that is the momentum lost by object A is equal to the momentum gained by object B. So take note that individually these objects have experienced a change in momentum. However, looking at the whole system, we see that the total momentum of the system has not changed. Object A before collision had 300 kilograms meters per second na momentum, and after collision, 0 kilograms meters per second na lang siya. And si object B had a momentum of 0 kilogram meters per second before collision, and after collision, 300 kilogram meters per second yung nag-gain niya. Okay, so individually, we see that A had a change in momentum from 300 to 0. Si B, a change in momentum from 0 to 300. But looking at the whole system, or the total momentum of the whole system, or both objects, we see that they are actually equal. They are the same. And this is what the law of conservation of momentum states, that the change in momentum, or rather the total momentum in a system is conserved or is constant. So the total momentum will not change even before or after a collision. That is why for this example, we can summarize the law of conservation of momentum using this formula. So we have the momentum of object A plus the momentum of object B is equal to the momentum of object A prime plus the momentum of object B prime. Okay, so where P prime represents the momentum after the collision. Okay, so at the left side of the equation, we have total momentum before collision, and at the right side of the equation, we have total momentum after the collision. And for generally for isolated systems, so when we have systems that have larger or have bigger numbers of objects to consider and their momentum, we write the equation simply as P total is equal to P prime total. Okay, so basically it's the same. At the left side of the equation is the total momentum of the system before the collision, and at the right side is the total momentum of the system, isolated system, after the collision. So in order for us to understand the law of conservation of momentum, let us prove it using its components. So let's start off with the force that each object apply upon collision. So we know that upon collision, object A will apply a force to object B, and object B will apply a force to object A. Now, Newton's third law of motion states that the forces both objects apply to each other would be equal in magnitude and opposite in direction. So if we were to write that down in a formula or in an equation, we would simply say that the force that A applies to B would be equal to the force that B applies to A. But the force that B applies to A would have a negative sign since it is in the opposite direction. Now, in collisions, we also consider the amount of time our objects are in contact with each other. And we can safely assume that in each collision, each object would share the same amount of contact time. So it is only logical that we say that if object A is in contact with object B for 1 second, object B is also in contact with object A for 1 second only. So we write that down as the time for A to be in contact with object B is equal to the time that B is in contact with object A. And interestingly, if we put these two together in an equation, we get the impulse of both objects. So recall that the formula for impulse is F times the change in time. Okay, so let's write that down. The force that A applies to object B times the change in time, or the time that A is in contact with B, is equal to, again, the negative of the force of that object B applies to A times the time that object B is in contact with object A. So we can simply write this as I, or impulse, of object A is equal to the negative impulse of object B. And if you recall as well, we have the impulse momentum theorem to help us relate our current equation with two momentum. So the impulse momentum theorem states that the impulse of an object is equal to its change in momentum. So our equation earlier can be rewritten in terms of momentum. And recall that momentum is mass times the velocity of an object. So for our equation earlier, since we have the impulse of object A is equal to the negative impulse of object B, we can write down the mass of object A multiplied to the change in velocity of object A is equal to the negative of the mass of object B times the times the change in velocity of object B, or simply the change in momentum of object A is equal to the negative change in momentum of object B. And we can see that both objects change in momentum have the same magnitude but are in different directions. And this basically proves that since the change in momentum of both objects in the system, object A and object B, are of equal magnitudes, there is no loss or addition of momentum in the system, but simply a transfer from or between the objects. Now, before heading on to our sample problems, let's first check if you understood our proving earlier. I'll give you 10 seconds to answer these questions, or you could simply pause the video and think about your answers. Okay, a large truck and a Volkswagen have a head-on collision. A. Which vehicle experiences the greatest force of impact? B. Which vehicle experiences the greatest impulse? C. Which vehicle experiences the greatest momentum change? Your 10 seconds starts now. Okay, so the answer to this question, if you truly understood our topic earlier, would be both vehicles will experience equal magnitudes of force, impulse, and momentum change upon collision. Now, if you need help to review, simply rewind this video or check out the slides later on in our website. So let's now begin with our first sample problem. A group of students are performing an experiment in class using collision carts on a track. So we have an 8.0 kilogram cart moving to the right at 4.0 meters per second, and it will hit a 4.0 kilogram cart moving to the left at 6.0 meters per second. Immediately after the collision, the 4.0 kilogram cart moves to the right at 3.0 meters per second. What are the speed and direction of the 8.0 kilogram cart after the collision? So we have here a before collision illustration that will help us understand the sample problem. And we have to remember that since we are talking about the law of conservation of momentum, ang kino-consider natin ay isang isolated system. And for this isolated system, we will only consider objects A, which is the 8 kilogram cart, and object B, which is the 4 kilogram cart. So we will only consider their momentum when we talk about the law of conservation of momentum for this system. And we also assume that the cart and the chuck, the friction between the cart and the chuck, is neglected. Okay? So wala sila, hindi natin i-consider sa problem na to yung friction between the cart and the chuck. Okay, so to recap, yung object A natin, which is 8 kilograms in mass, is moving to the right with 4.0 meters per second, while our object B, with 4.0 kilograms as mass, is moving to the left with 6.0 meters per second. And recall our notation last week, the velocity of our objects would have the following signs. So yung object B would be negative ang kanyang velocity since it is moving to the left, and our object A would have a positive value for its velocity since it is moving to the right. So we will use this notation once again all throughout this lesson guide. Now let's take a look at the after collision. The after collision, we have object B, which is moving to the right at 3.0 meters per second, and our object A, which is moving in an unverified pa na direction and an unknown speed. So basically, ang hinahanap natin dito is yung velocity ng ating object A. So we don't know yet whether it's going left or right, but we will be able to identify that later on when we get our final answers. So again, let's remember our notation. If it's negative, it's moving to the left, and if it's positive, it's going to the right. So if our final answer would have a negative value, we would consider that our illustration here, our assumption here is correct, that it's moving to the left. And if it has a positive value, our final answer is a positive value, then the object A, or the 8 kilogram cart, should be moving to the right. Okay, now let's proceed to our GRESA method. So let's first identify the given. So we have the mass of object A, which is 8.0 kilograms, and the velocity of object A before the collision, which is 4 meters per second. We also have the mass of object B, which is 4.0 kilograms, and its velocity before the collision, which is 6.0 meters per second. And we're also given the velocity of object B after the collision, so VB prime, at 3.0 meters per second. And the question once again asks us for the speed and direction of the 8.0 kilogram cart, or object A. So we simply note that as the velocity. So the velocity of object A after the collision, so VA prime. And for our equation, let's recall that our law of conservation of momentum uses the equation P total before the collision, or the total momentum before the collision, is equal to the total momentum after the collision, so PT prime. And if we expand this equation, we get the equation mass of object A multiplied to the velocity of object A plus the mass of object P multiplied to the velocity of object B before the collision is equal to the mass of object A to the velocity of multiplied to the velocity of object A after the collision, so prime, plus the mass of object B times the velocity of object B prime. So there, we have this expanded equation, and we will use this expanded equation to isolate our value of velocity of object A after the collision, so the required. So we will be using this equation to isolate V sub A prime. Just to show you How will we isolate this? So let's manipulate our equation. So first we move this value to the left side of our equation by simply subtracting it to both sides of the equation. So we have the mass of object A times the velocity of object A plus the mass of object B times the velocity of object B minus the mass of object B times the velocity of object B after the collision prime is equal to the mass of object A times the velocity of object A after the collision. So we have this value isolated, and now we just want the velocity of object A after the collision again. So we will simply divide this, or divide both sides of the equation with the mass of object A after the collision. So we can simply cancel this, and so we have here our working equation. And for our solution, we will simply substitute our values with our equation. So 8 kilograms times 4 meters per second plus 4 kilograms times 6 meters per second, negative 6 meters per second since it's moving to the left, minus 4 kilograms times 3 meters per second over the mass of object A, which is 8 kilograms, is equal to our required value. And if we simplify this further, we will get negative 4 kilograms meters per second over 8 kilograms is equal to the velocity of object A prime. And if we further simplify this, we can cancel kilograms, and we are left with negative 0.5 meters per second. So therefore, this is our answer. This is our final answer. And to answer the question, the speed of object A, our 8 kilogram cart, will be 0.5 meters per second, and its direction would be moving to the left. So our assumption in our illustration earlier was correct. Now, in order for us to check if our final answer is correct, we simply substitute this value with our general equation earlier and check if both sides of the equation are equal with each other. Now, for our second sample problem, we have two adjacent students standing on stationary skateboards. They are facing each other and they push apart. The student on the left weighs 65 kilograms. The one on the right is 85 kilograms. If the lighter student moves at 3.2 meters per second, determine the speed and direction of the heavier skateboarder or student. So again, we have here an illustration. So for this problem, we will label student A as a student with 85 kilograms of mass, and student B, the student on the right, or the student with 65 kilograms as mass. So we have here, they are stationary, so they are not moving. So this is before pushing each other. And afterwards, we see that object B, or student B, moves to the right at 3.2 meters per second, while object A moves to possibly the left or to the right, which we will identify later with our final answer, with an unknown speed. So again, this problem, just like earlier, is asking for the velocity of object A after pushing each other. But the difference is, this instead of collisions, our problem presents us with a scenario where the objects are pushing each other apart. So let's see how the law of conservation of mass is observed in this scenario. So let's proceed to our GRESA method. So let's first list down our given. So our given is the mass of student A, which is 85 kilograms, and the mass of student B, 65 kilograms. And lastly, the velocity of student B after pushing, so VB prime, 3.2 meters per second. And what's asked in this in this problem is again the velocity of student A after pushing. Now for the equation, let's once again recall our generally expanded equation earlier, which is the mass of object A multiplied to the velocity of object A plus the mass of object B multiplied to the velocity of object B before pushing each other is equal to the mass of object A multiplied to the velocity of object A after pushing plus the mass of object B multiplied to the velocity of object B after pushing. So again, we have before pushing and after pushing. Now, to help us make things easier, so since the students were not moving at the beginning, we will automatically assume that their velocities will be zero. And if we have zeros here, automatically the value inside these parentheses will be zero. So automatically this side of the equation would already be zero. So our equation now would be 0 is equal to the mass of object A and the velocity of object A, their product, plus the product of the mass of object B and the velocity of object B after pushing. So we will have to manipulate this equation to once again find V sub A prime, or the velocity of object A after pushing. So once we have successfully manipulated, we will have a working equation of the mass of object B times the velocity of object B prime over the negative mass of object A is equal to the velocity of our object A prime. So this is also the mass of our object A prime. Again, for our solution, we will now simply substitute our values in our working equation. So 65 kilograms, the mass of our student, times its velocity after pushing, 3.2 meters per second, is equal to the mass, it's divided by the negative of the mass of our student A is equal to the velocity of student A after pushing. So we simplify this further, we will get 208 kilograms meters per second over negative 85 kilograms. And if you want to simplify that, simply cancel the kilogram units. And we are left with our final answer, which is the velocity of student A after pushing, or V sub A prime, is equal to negative 2.45 meters per second. So basically, our student A is moving to the left since it's a negative value at a speed of 2.45 meters per second. For our last sample problem, I'll be focusing more on the technique or the process on solving this sample problem, which you can always apply into the different problems you will be encountering in answering problems considering the law of conservation of momentum. So for this sample problem, a baseball sits on a T-ball stand. A child hits it with a bat moving east at 6.0 meters per second, and the ball flies off at 15 meters per second. Now determine the speed and direction of the bat immediately after impact. The T-ball equipment is smaller than regular baseball equipment. And the ball weighs 125 grams while the bat weighs 500 grams. So we have here again a before and after illustration. So it is helpful that we are able to imagine, visualize our problem. So in solving these kinds of problems, it would be nice if you could draw simple diagrams that could help you visualize the objects moving. So before the collision, we have the bat, our object A, and the ball, our object B. So it's important, or it's helpful, that we label our objects properly. So we label objects A, object B. So later on, when we write the given, we can label our values properly. Okay? So again, our object A is moving towards the east direction with a 6.0 meters per second speed and a mass of 500 grams. And the ball is 135 grams. It's not moving. So currently, or before the collision, it has a velocity of 0 meters per second. And afterwards, we see that the ball, after collision, moves towards the east direction at 15 meters per second, with retaining its mass. And the bat still moving at the east direction, but with an unknown speed. So our work again here for this sample problem is to find VA subprime. So similar to our first sample problem. Now let's proceed to our GRESA method. So again, the technique here is we start with the given. So since we've labeled it properly, we can list down our values properly. So the mass of object A, so the bat, is equal to 500 grams, and its velocity before the collision is equal to 6.0 meters per second, while the mass of the ball, object B, is 125 grams, with a velocity the velocity before the collision is equal to 0 meters per second. And remember, we use the prime notation to note that this is the velocity of object B of the ball after the collision, which is 15 meters per second. So again, we're required to find the velocity of the bat after. So VA prime. And for our equation, this is the same as the equation we used earlier in our sample problem 1. So how do we again get that? So the main tip here is that we should put to heart or memorize and be able to recall the general and the expanded equation we use for the law of conservation of momentum, which is the following. So once we have this in mind and we can write this down with our eyes closed, yan, kaya na nating i-manipulate tong equation na to para mahanap yung mga variables na hinahanap sa bawat problem. So for this sample problem, again, it's the velocity of object A, or VA prime. Earlier, we discussed how we got this, how we manipulated the equation. So you can just rewind that. And again, you can apply this in any sample problem. Kunyari, ang ibang sample problem, ang hinahanap is yung velocity required before the collision to have this amount of velocity. Ganyan. So ang hinahanap is yung velocity ni object B before collision. So you can just manipulate this equation to find the working equation you'll need later on for your solution. Okay? Once you are able to work out your working equation properly, rearrange the general equation, you can easily substitute your values from your list of given values to your working equation. So we have here yung ating substituted values, and then we simplify them, and you get your final answer, which is 2.25 meters per second. So again, remember to always put your units and cancel them properly so that you can verify if, since velocity yung hinahanap and you're left with the unit meters per second, you are assured na tama yung ginagawa mong process. And you get the final answer of, again, 2.25 meters per second. So the speed of the bat after the collision is 2.25 meters per second and is moving to the east since it's positive. So again, remember to practice the use of the proper signs since it will determine the direction of your object after or before the collision. We also have to take note that in this problem we are given the grams of the objects, but we need to use the standard units of kilograms. So we have to simply convert our units to the appropriate units and use that in our equation. And again, if you always want to check your final answer, aside from the units, be as a hint, you can always substitute your final answer to your equation, to the general equation, and see if both sides of the equation would have the same value. And if they do, it means you got the right answer. Now, let's head on to our supplementary materials. So we have here a cart and brick interactive by the physicsclassroom.com. So you have here different scenarios of a brick falling down a cart of varying mass and velocity, and the students will be allowed to manipulate these collision scenarios and observe the total momentum before and after each collision. So you'll see that in different scenarios, you will see that the total momentum before and after should be equal. And if you want to still learn more about solving sample problems on law of conservation of momentum, you can visit this video by the organic chemistry tutor titled Conservation of Momentum Physics Problems, Basic Introduction. And it's a video tutorial and guide on solving law of conservation of momentum physics problems and highlighting the role of force in transferring momentum. So in this video, you will be able to encounter his interpretation of how momentum is transferred from one object to another through force. So find out more on this video, and here are our references. Again, this is Mark Cortez from Filipino Science Hub Ed, and I would like to thank you for watching. If you have any suggestions or any request topics, please comment and we will try to accommodate those topics. Thank you for listening and have a great day.